I tried taking notes during all of the panel presentations to see what was going on and decided I needed an organizing theme across the many different topics that were presented. So I took the theme as I would take ideas from each of the panels that I could use to try and invent the future, namely what would be a digital library in 2050. So we had these following panel sessions, and they covered a wide variety of topics, from how to build a repository, how to cite data, how to build support within your own institution, the business plan and models for actually paying for such a library, what sustainability might mean, how to train the next generation of data practitioners. So each of these panel sessions had a variety of topics that were presented. And if I look at them, I can highlight in red ideas that might help define what a digital library in 2050 could look like. So in the first panel, we went through data management plans and policies. How do I organize, how do I plan, how do I manage a repository? And basically there are a wide variety of rules and regulations, assertions you want to make about a collection that you'd like to be able to either enforce or validate. When you work with very large collections, you can spend all of your time in administrative functions if you're managing a petabyte of data. So you would like to be able to pull out of these data management plans the policies you actually wanted to enforce, how to be able to automate the set of tasks to minimize the labor required to keep a large-scale digital library running, and how to go through and validate that the library is working correctly. So those are some topics we would want to use in 2050. Another set of topics that we went through were on data identifiers, and we recognize that unless we can identify the objects we have in our collection that we're providing to users, nobody will be able to either know what they are or be able to discover them. And the challenge is that I can't just use a URL because that links the data to a location. I need some location-independent mechanism that's automatically updated when I move the data around. I will never have a situation where data can sit on a single storage resource forever. Every 3 years I buy the cheaper version and it's going to move. So I need an identifier that allows me to continue to have a unique representation for that data, but as it moves, that unique identification remains valid. And then we have the challenge of what type of identifiers do we develop. We want an identifier for scientific data, but you could just as easily have an identifier for a process that created the data. So the workflow that applied, took the raw data and transformed it, I could re-execute that workflow if I had an identifier for it. Which brings us to this issue of what does the identifier actually represent? Does it represent the data or the context for the data? And without a context for the data, then I have a very hard time interpreting what the data is. So if you look at that in a little bit more detail, there are the standard NASA levels from raw data to calibrated data to physical quantities to projected in a coordinate system. And each of those is a transformation on the original raw data. If I change the calibration mechanism, discover a problem with the prior calibration, I would like to be able to reapply it and therefore be able to re-execute any of these steps. So we would like to be able to identify the process that created the data as well as the result of running that process and be able to re-execute that workflow. To do that, there's a major challenge, which is how do I run somebody else's workflow which was created for a specific hardware-software environment. When we work with data, we've abstracted the data away from the storage system. The data is zeros and ones. I can move those zeros and ones to another storage system and still interpret them. How do I move a workflow to another computing environment and still be able to run it? So we want something that would be called workflow virtualization that would allow us to re-execute our processes on the technology we will have in 2050. Another topic that was discussed was curation service models. We have many instances of how we bring one of these curation service instantiations into existence. Basically, they're driven by the user requirements. We discover what our users need and then build a data management application that addresses those requirements. But there are many different sets of requirements depending upon what you want to do with your data management application. And we heard a variety of applications here, from institutional repositories to groups that are trying to build national infrastructure to groups that are building domain-specific repositories. Is there generic software that I could then apply in any of those instances, and what would I have to modify with respect to that generic software to build my next management application? So one way to do this is to think in terms of a particular data management application, in terms of the access methods, the policies, and the procedures you're actually going to run. And if you have a system that allows you to vary the policies, procedures, and methods, then you could tune that infrastructure to the next form of data management application. And the other topic that was presented in this panel was the fact that even if they start small with a small number of communities, they can extend, broaden their data repository capabilities by working with another community, broaden the number of communities that are being supported by your particular institutional repository. So this gets you to the idea that the institutional repository itself is going to evolve. It started out responding to the needs of a small number of users, and now we're making the community broader. We're supporting a wider range of domains, and therefore we have to have our capabilities within our digital library evolve to handle the new situation. Another topic that was presented is basically about the types of services we implement for our data management application. Everybody does discovery, everybody does access. Everybody now, if they're playing with scientific data, will have to start worrying about data manipulation. When the researcher accesses the data, what do they really want to do with it? Are we going to force them to take a copy of the data somewhere else and do all the manipulation on their own platforms? Or will we provide services that allow them to manipulate the data directly within the digital library? The typical data manipulation mechanism is subsetting. I don't want the entire 2 megabyte file, I want a very small 10 kilobyte subset. So I've got to be able to run a process at the digital library that allows me to manipulate the data and extract the part that's of interest. But there are many different types of data manipulation. So if we go back to the idea, do I want the raw data or the calibrated data? If the calibration changed, then I want to be able to rerun the analysis that converts the raw data to the new calibrated form. I may want to transform the data to another type of format. I may want to do something more sophisticated and detect features that are present in the data. If I have a climate model, do I see an El Nino effect within that climate model? Given a set of features, then I want to index the data based on those features so I can now discover in the future all the particular climate models in which the El Nino effect was present. My other challenge is that the data I'm working with isn't reality. It's some snapshot of reality. And therefore, if I'm manipulating the data and it's on one particular set of points in space and time, I may want to interpolate between those points in space and time to other locations. So I don't want to work with the data, I want to work with the data model. I want to work with the polynomial that's fit to the data such that I can then map it to my particular use. For sustainability, a challenge was identifying which community is interested in sustaining the contents of the digital management of the digital library. Given the identification of an appropriate community, how do you quantify the benefit to them? How do you invent a cost model such that they're willing to support it? They view that the benefit will outweigh the cost to them. And how do you go about minimizing that cost such that you can make it more attractive to a broader set of communities? So one of the mechanisms is to try to automate the more costly aspects of building a curated environment. Can you automate curation itself? And the answer typically is doing curation requires domain expertise. The only way I can easily automate it is to have the domain expert run a procedure that provides the required information so the librarian doesn't have to do it. A nice example is a FITS model. It tells me it's basically a standard format for an astronomy image, and it has a header in which there's metadata describing not only all the attributes of the image, which direction was I looking, but it also has metadata that can describe the observatory and the project under which the image was taken. So in that case, in the FITS file, I can get provenance information for the context. Why was the image taken? What was the project for which it was developed? And you really would like the domain scientist to be providing that level of context with every set of data they generate. Right. So Microsoft, okay. Let's go back. So we're pulling ideas from each of these different panels, which might be appropriate then for deciding how to go about creating the digital library in 2050. So I think I was here. One of the challenges then is each of the domains we're working with has a different set of services they want to apply on their data, because they want to be able to manipulate the data as well as discover it. Each of these services then are driven by specific sets of requirements for some community, and you end up in a situation where each time I'm going to implement a digital library, I might force myself into a situation where explicit services required by that community or what I have to provide, and that differentiates that application from the other. But we had the concept that curation was really a continuum, that what we're trying to do is provide a variation of application environments from groups that are trying to share data, take the same data into an environment where they're publishing it for use by others, take it into an environment where they're trying to do a long-term preservation as a reference collection. So we can do this if we can support characterization of a domain in terms of the methods, policies, and procedures that are used to manage it. And the challenge then is that the methods and procedures we're applying are going to evolve in time as a set of communities for which we're trying to support become broader. So the digital library, the data center itself, is going to have to evolve over time. So we've gone through sustainability, creating a library, benefit of scale. One of the things we heard about is that one of the benefits you can provide to your communities is the fact that as you aggregate data into a center, it's cheaper to do the administration than if you have 100 different smaller environments. A final set of panels were on educating the next generation. Can we identify what we should be teaching, what curricula we should be providing, such that the students or the next generation will be able to design the appropriate digital library for use in 2050. And there are two aspects to this. One is in terms of developing curriculum, how do we couple explicit research to the educational objective? We've heard many examples where if you tied the digital library application to a specific domain and then showed the application of the techniques within that domain, it made everything concrete, more palatable to the students. The other is that we're still trying to understand what data-intensive science means in terms of what are we actually providing when we're providing data, how is that data linked to the context within the domain that generates it. Is it a skill that we develop in order to do the manipulation, or is it, and can we teach that skill to an arbitrary set of people, and therefore think of the education as skill development rather than a specific domain problem? When we work with students, the typical challenge we always hear is that if a student is having to do a problem on data somebody else has analyzed, then it's uninteresting. They're working with dead data. If it's live data, it's data that somebody else has not already analyzed, and they can make a discovery. If they can make a discovery, they can get excited about the research, and they can say, oh, I can see why people would want to do this. So for education, then, one of the major challenges is getting research data that's still in process into the education initiative so it can be analyzed by the students, which means that in practice I need the policies and procedures that the research community believes are appropriate for transforming the data into an acceptable form so the students won't make erroneous discoveries. The data will be in an appropriate form suitable for a student to look at. So we've been trying to develop technology that we could use to build the digital library of 2050. And our challenge was, when we started, we had to decide what we were going to do, how we were going to manage data. So we chose to virtualize the collection. We wanted to manage the properties of the collection itself rather than virtualizing the storage. When we virtualized the collection, we had to differentiate between, are we managing bits and storage systems? Are we managing information about the collection, attributes we put on each item? Or are we manipulating knowledge? So we had to come up with a way such that within a computer science environment, we could differentiate between data, information, and knowledge. So we picked this particular mechanism. Data is the set of bits. There's some approximation to reality. So I have some model on which I'm basing the extraction of that data, the recording of that data. If I've got a sensor, then it's the calibration of that sensor, the resolution of the sensor, where that sensor is placed, and it will get me back some data. But that data has a meaning in terms of that context. If it's a simulation, then it's the resolution of my simulation. It's the physical model I was running to generate that data, but it's a set of points typically in space and time. If I want to put any information on the data, I'm actually assigning a label. To assign a label, I have to know whether or not the label really applies, which means there are a set of relationships that have to be satisfied. So I have an object over there which is rectangular, it's got a hinge on two sides, it's got a knob I can turn, it opens and closes. If it satisfies all those relationships, I call it a door. So any term I'm using to describe scientific data has an implied set of relationships behind it. So we think of information as the application of the label. We think of knowledge as the ability to evaluate those relationships and decide whether the label can be applied. And therefore we build this simple representation. Data are the bits we can manage in the distributed environment. Information is the metadata we put on those sets of bits. And knowledge are the relationships we evaluate between labels. To evaluate a relationship, I have to be able to run a procedure, manipulate the data to see if that relationship is present. So in the IRODS environment, then, we express knowledge through workflows that evaluate the relationships so that we can then assign an attribute on the data. So now we can think about what would a digital library be in 2050. We know the technology is changing extremely rapidly right now. We're getting to the stage where we do item-level indexing, we do item-level searching, we search even on words within items. So we're getting down to the actual manipulation of data at a very fine scale. We have the ability now to manage massive amounts of data, which means we can build a collection that covers the entire phase space, i.e. every possible instance of a set of data could be in a collection, so I can then not have any missing holes that I haven't analyzed all the data there that I might need. So in text, there are only 15 million English words. This is the number of words that appear more than 100 times on some web page somewhere in the world. Most of them are misspellings. The cultural knowledge that we deal with in humanities is less than a terabyte, more like 100 gigabytes. So when I did the Watson demonstration, they had a relatively small database which they had to index more than 100 different types of relationships. So they had spatial and temporal and organizational and familial relationships they applied on the data, and then they could take a natural language query and then find an answer in a relatively small database. So a terabyte of data is no longer large. And then we have the challenge now that we can put many different types of relationships across that data. We don't have to restrict ourselves to just looking for words. We can look for relationships, either in any of these particular domains, whether it's spatial or temporal or semantic relationship. So what we would like to think of in 2050 then is a digital library which is continually extracting features from the scientific data sets that are being put in, that's generating an index based upon the features that are detected. So I query the collection for a feature rather than querying the collection for an individual data set. That links the local feature set to the external feature sets being defined by the community, which means now I have a knowledge base. I've got my data, I've got a characterization of my data, I know how it's related to the data used by the rest of the community. And I have an environment in which I can define new sets of relationships that I can have the system automatically apply, extract new features, allow me to construct a new index. So if a researcher comes in and says, I now, instead of an El Nino effect, want to look at a La Nina effect, I can go in and now analyze the data and present an index based upon that new analysis. So the implications then are that we're going to characterize scientific data by the workflow that creates it. So I have to be able to register workflows, manipulate workflows, in addition to manipulating data. Those workflows are the mechanisms by which I extract knowledge from the data, analyze relationships, determine whether a feature is present. And then in order to do that, I have to have the ability to basically virtualize a workflow. I need to be able to run that procedure on any operating system. The same procedure's got to run on Windows, on Mac, on Unix, etc. If we do that, then we can build an environment that is appropriate for 2050. It represents data as searchable metadata. It represents the model of the data, so I can manipulate at an arbitrary point in time the original data. It gives me a context to define the approximations under which the data was generated, the physical model it was supposed to represent. We can then virtualize the collection to manage the properties of a collection. We can virtualize the workflow, manage the properties of execution of the workflow. So that's the final viewpoint. A digital library in 2050 enables us to link the content to a knowledge repository represented by our community of interest. It'll have an index that's probably terabytes in size, but we're at the point now where a terabyte of index is relatively small for a collection that's petabytes in size. We'll be able to analyze the contents, so the library dynamically recreate these indices. It means that the researcher now has an opportunity to conduct many of their activities within the library instead of extracting their data from the library and having to do it at home. So this is a major change in scenario where the library is thought of as not only the repository where I put the data, but now it's the repository where I can run the analyses, such that the library then becomes the fundamental support mechanism for the researcher. It's no longer a cottage industry where every researcher goes to their own local server and tries to do everything themselves. There's an institution behind them now, the library. So that's a very aggressive view of what libraries will be. It means it's not just data anymore, it's also the processing, it's the ability to manipulate the data, it's the very tight coupling of data with the capability to analyze it. Thank you very much.